Welcome everyone to this week's edition of our College Credit webinar series. Today we are discussing CEP distributed processing on Cassandra with Storm. This is a technology mix that in the community we see increasingly more and more of. And I am very excited to say that today we have two speakers with us. We have Brian O'Neill, who is the lead architect at Health Market Science, and he is an MVP for Apache Cassandra, very well known in the Cassandra community. And also joining him today, we have Taylor Getz, and Taylor is an expert in Storm and has been in the Storm community since it was open sourced. And he has been leading the charge around Cassandra and Storm integration. A couple of housekeeping items. We will take Q&A at the end of this session. So if you have any questions for Taylor and Brian, please use the Q&A tab inside of WebEx and put your questions in there, and I will ask them at the end. Also, we are recording today's session. The archives of our webinar series are available at both datastax.com and also our community website, planetcassandra.org. And without further ado, I will hand it over to Brian. Thank you very much for joining us today, Brian and Taylor.
Hey, no problem. You're welcome. All right, so I'm very excited to do this presentation. We did the last webinar was you can create your first Java application. This one, we're taking it up a notch. And you know, if you're familiar with Cassandra and you're familiar with the CRUD operations on it, this is taking it to the next level. And once you've got your data in Cassandra, what can you do with it? And kind of analytics can you perform? How do you integrate it with the other systems in your enterprise? So without further ado, we're going to get started. All right, the quick agenda is I'm going to go through the use case, sort of talk about what complex event processing is, what would you use it for, sort of get motivated to deploy Storm, and then I'm going to hand it over to Taylor. He's going to do a little bit of background on Storm, how to deploy, what the cluster looks like, go through some code and do a demo, and then if we have time, we're going to come back and talk about sort of new things out in Storm, specifically Trident, which is a higher level API that we've recently adopted, and we're migrating all of our topologies to Trident. So first, our use case. So our main product is called a master. Is mentioned in two different feeds with two different addresses. Which is the best one? Pick that out and then report out on all the answers and the quality of the master file. So that's a challenging problem to solve. It's really valuable in that once we have that master file, you know, pharmacies can use it to determine if a prescriber is eligible to write a script. But there's a lot more involved than just CRUD. So when we take a look at it, reason we put Cassandra in place, like I was saying, is that there's thousands of feeds. Those schemas can change over time. It's quite a bit of data, but to us, the major motivating factor there to select Cassandra was the variety of data. So what we do is we take those thousands of feeds, we dump them into Cassandra, run all sorts of analytics and things, and then produce a master file that we deliver to our clients or provide web services integrations for them. So if we have Cassandra in place, what didn't that cover? Well, you want to be able to search that data.
Hey, Taylor, sorry to interrupt. So showing on the screen is still the presentation that I led in with. So are you sharing your desktop?
Oh, good. I believe we are. I'll share. There you go. Yeah.
How's that now, Kristen?
Yeah, now we're getting there.
Much better. Okay, so I'll just show you the pretty pictures real quick.
Yeah, people were having to close their eyes and imagine. So,
all right.
This is great.
So no problem. So here's the agenda. Like I was saying, it's just the use case, then hand it over to Taylor, and then come back for a little Trident if we have time. And then here's the doctor that we've got. The industry and the capability that we're in is called master data management for all those feeds. And then, like I said, we deployed Cassandra to handle the variety of data and a bit of the volume. But that didn't cover all of our requirements. So now that we're here, we needed to supplement Cassandra with a few other things. Specifically, we needed to be able to search unstructured data. So fuzzy matching on addresses, for example, geospatial kind of queries. We also needed real-time analytics and reporting. So that data that was in Cassandra was great, but we needed, dimensional counts, aggregate counts. So how many doctors of this specialty are in this area that have sanctions against them, for example. And then also transactional processing. So, we have a web front end, and we wanted that data to be immediately searchable, right? So, and reflected in sort of wide row indexes that we were maintaining. What does that look like? So this goes into a little bit of our infrastructure from a very high-level logical point of view. About 2 years ago, we looked at the different searching indexing engines that were out there. And I think everybody knows the two that are most prominently deployed are Solr and Elasticsearch. Solr is great. We actually chose that first because about 2 years ago, we didn't think Elasticsearch was mature enough. We've changed that opinion. So Elasticsearch is one of our integration points now. That tends to scale like Cassandra does. So it handles replication and distribution underneath the hood rather than with Solr where you had to manually do it. Then we have web services, right? So we chose DropWizard for that one. And then we also want to be able to do reports. So, and most of the reporting mechanisms, although DataStax is got some good integration with Jaspersoft, most of the reporting tools still go off of relational. So if we take this as our use case, let's walk through a couple of things. This is where we wanted to get to, but we're going to go through a couple of things that we did wrong before we got here. And the first was Hadoop. So this is not to knock Hadoop. We love Hadoop, but its focus is a lot around batch processing, right? And when we looked at our problem, we wanted to be able to reflect changes as they happen transactionally, and we couldn't do that well. Just spinning up the Hadoop job was longer than we wanted it to take to be reflected in the user experience. So that wasn't going to work. And then in order to effectively kick off those Hadoop jobs, you also needed to track what changed in the system, so what goes into that batch. So that added a little complexity that we didn't like. So then overall, some of the processing that we saw to race over column families that contained our data was just too long for our tolerance. So what we did wrong part two. So we moved to a AOP triggers approach. So we liked that. It took all the burden off of the clients. So we actually used an AOP extension that we open sourced called Cassandra Triggers that would watch data as it changed in Cassandra and update some wide rows. So that was great. That worked really well. But then we realized as we integrated more and more systems and wanted more and more wide rows, that became a huge burden on the right in Cassandra. And then in addition to that, guaranteeing the execution of those triggers to make sure you had guaranteed processing those triggers was extra overhead. So we turned towards complex event processing. So just a tiny bit of background on event processing. This is straight from Wiki, so standard throw definition on the slide thing. Complex event processing is a matter of treating the events like streams, right? And then discovering different things from that stream, those streams of information. So if we take our use case and frame it as a complex event processing problem, our events in our system are CRUD operations, as they either happen in the system or want to happen in the system. So if you take that frame of mind, the complex event processing can become an ETL tool and or analytics. Take a second for that to sink in. And then what that means is that you can take a complex event processing engine and apply it as a data processing pipeline. So if we go back to our original, here's where we want to get, so our users are happy, right? And we take a complex event processing engine, and you have the CRUD operation coming in. You could take that piece of data, transform it before you write to your system of record. So in our case, our system of record is Cassandra. Then continue to pass that event down the line to do dimensional counts. So aggregate the different dimensions on the data that's coming through. You could then enrich that data by touching other systems and pulling in extra metadata, and then write it to a fuzzy index, right? So this is a really powerful, turns out, and we really like what's going on, and it pulled all of that complex data flow that we were embedding in different applications and clients out to something that was manageable and tangible that we could reason about. So that's one of the powerful pieces of Storm, that these topologies, and I'll let Taylor go into the details of it. The topologies actually articulate your data flow in the system. So that's great, and allows you to do some really, really cool stuff. So I will, at this point, hand it over to Taylor, and he'll take you through the details.
Okay. Thank you, Brian. So just to start out with a quick overview of Storm. Storm is a distributed real-time computation system. So it does complex event processing type work. It was open sourced by Twitter in September of 2011, and that worked out well for us at Health Market Science, because about that time is when we started moving away from batch processing into a more transactional real-time processing model.
Hi Taylor, this is Christian. Sorry to interrupt. Could you speak up a little bit or get closer to the microphone?
Sure. Is that a little better?
Yes, that's a lot better. Thank you.
Okay. Storm is fault tolerant. It's distributed among multiple nodes, and I'll get into more of the architecture a little later, but you can have nodes go down and Storm will continue to process data. It's highly scalable horizontally. Much like Cassandra, you can scale by adding additional nodes to your cluster. Storm supports a model of guaranteed processing, so that when your data streams, events within your streams, if for some reason fail to process, they can be replayed, so that processing is guaranteed. And in terms of CEP, Storm operates on one or more streams of data. So you can have any number of inputs into your distributed computation. The anatomy of the Storm cluster, the diagram you see is a typical development cluster that we use here at HMS. If you're familiar with Hadoop, then this layout will look fairly familiar. There's a master node in Storm language that's called Nimbus. And then there are slave nodes, which are essentially your worker nodes. In our development clusters, we also put Cassandra nodes on our slaves. So there's also an assistant node, and for our clusters, that's where we run Zookeeper. And what Zookeeper does is maintain the state of the cluster. And then supervisors are Storm daemons that actually run the tasks that make up your data processing. And I'll get into more of how that works in subsequent slides. But Nimbus's job is to assign tasks to the supervisor nodes. And that can be multiple workers and multiple tasks. And master also, through Zookeeper, keeps track of the health and state of those daemons. So if one daemon were to go down, or say you lost a node, master would take the workers and reshuffle them among the slave nodes. Storm components, the source of data entering into your computation comes from Spouts. Spouts are essentially stream sources of data, and I'll expand on each one of these later. Bolts in a storm topology are your units of computation. So they do operations or react to the data that's passing through the system. And then a topology is a combination of any number of spouts and any number of bolts, and it defines the overall computation or computation network. So to expand on spouts a little bit, as I mentioned earlier, spouts represent a stream of data. Examples of that could be queues, like a JMS queue, Kafka, Kestrel, etc., or something like the Twitter Firehose, or sensor data. I know the Weather Channel uses Storm to process weather information. So a Storm spout connects to some sort of source stream or queue and emits tuples, which represent the events in CEP language. And tuples are the primary data structure in Storm, and they're basically just a set of named key value pairs. Storm bolts are responsible for receiving tuples from spouts or other bolts, and they operate or react to the data. So bolts are typically something you provide or provided for you, and they can perform functions, do filtering, joining, aggregation, that kind of thing. And they can also do database writes and lookups, which is where Cassandra will come in a little later. And then bolts can also optionally emit additional tuples. So if you have a spout that's emitting tuples, the spout will send those to one or more bolts, and then the bolts can either just react to that data, or they can emit additional tuples. And I'll get into more of that later on. And storm topologies represent the data flow between spouts and bolts, and routing of tuples between spouts and bolts. The routing is basically a simple subscription model, and when you define your topology, you define groupings, and what groupings do is determine how tuples get routed between bolts and spouts within your topology. One of the groupings that I'll get into later on that's very important is what's called a fields grouping. And what that does, because both spouts and bolts can be parallelized, so given a bolt in a topology, you can define how many instances of that bolt you want to be active in your topology. But when we do stuff like filtering and aggregations, it's important that sometimes the same field content goes to the same bolt. So a field grouping helps accomplish that. And basically the way that works is probably those who are familiar with Cassandra will understand the concept of a distributed hash. So basically it just hashes the values of the fields that you specify, and that determines which bolt it will pass to. Storm topologies are long-lived, unlike a Hadoop job, which is a batch process that has a start and an end. Storm topologies run forever until you essentially kill them. which is understandable because your stream of data is open-ended. So Storm and Cassandra. Some of the use cases that we looked at were being able to write storm tuple data to Cassandra. Examples of that would be computation results or pre-computed indices. And then also to read data from Cassandra and emit storm tuples. So that kind of thing would enable us to do dynamic lookups, essentially have a tuple come in and based on the data in that tuple, do a lookup or a fetch to Cassandra, and then based on those results, emit additional tuples. So in Storm Cassandra, we have two bolt types that I mentioned earlier. There's the basic Cassandra bolt, and what that does is take tuples passing through a storm topology and persist the data to Cassandra. And then we have Cassandra lookup bolt, which does the opposite. It pulls data out of Cassandra and emits tuples based on that data. The Storm Cassandra project, which is open source on GitHub, provides generic bolts for reading and writing storm tuples to and from Cassandra. And the way we did that was come up with the concept of mappers. So we have the Storm Cassandra project is essentially a framework that defines generic bolts, and then you provide a tuple mapper or a columns mapper that is specific to your use case or your data model. So by plugging in a mapper, you get all the benefits of the framework, and all you have to concern yourself with is the implementation of your mapper. The framework does the rest for you. So the tuple mapper interface tells the Cassandra bolt how to write a tuple from an arbitrary data model. So given a storm tuple, you would map to a column family. So basically, you tell it which column family you want to write to. Map to a row key. That allows you to determine what your row key is based on the content of the tuple. And then map to columns. That's mapping how the data in the storm tuple gets stored in Cassandra columns. Then on the opposite direction, the columns mapper interface tells the Cassandra lookup bolt how to transform a Cassandra row into a storm tuple. So given a Cassandra row key and a list of columns, it returns a list of storm tuples. The current state of the Storm Cassandra project, right now we're working hard on version 0.4.0, which is a work in progress. It's currently using the Astyanic client. We have a couple out-of-the-box mapper implementations, a basic key value column mapper for basically like a hash map type data model for Cassandra. Valueless columns, that's a common data modeling pattern in Cassandra, and I'll demo that later. We just added support for counter columns, lookup by row key, and also lookup by range query. We're just beginning to get into Trident support, and a little later I'll talk more about what Trident is. And we also have an initial pass at composite columns. Future plans, we're thinking about switching to CQL, and then also we want to support Trident fully. Before I know I went pretty quickly, before I get into a demo, are there any questions? So the first demo I'm going to do is a word count, and this is sort of one of the canonical examples that is used for both Storm and for Hadoop. The idea is that you have a spout that's emitting random words. And from there, it goes through a fields grouping, to a counter bolt that keeps account of each word and how many times that word's been seen. And the importance of using the field grouping there is if the count bolt is parallelized across multiple nodes in the cluster, you want to make sure that the same word goes to the same bolt, otherwise your counts would get out of whack. Then from the count bolt emits essentially the counts of each word in real time as they're incremented, and shuffles them to the Cassandra bolt, which is responsible for persisting the count for each word. So now I'll get into a demo of that.
And
so right now,
Taylor, as you're doing that, there are some questions, but we'll just hold all of those until the end.
Yeah, I figured that. Thank you. Okay, so right now I have a storm column family that is empty right now. And what I'm going to do is pop over to Eclipse and run the persistent word count topology. And this is just a couple lines of code, and I'll walk through that after I run it. Okay, now that the topology is running, so it's actively spitting out random words, and actually, I think in this demo they're names. And if I list that column family again, we'll see the words and a corresponding count. So the row key of Nathan, you can see that as of that query, that word had been emitted 56,000 times. Then there's Mike, Jackson, and a couple other names. And if I run it again, we'll see that that incremented much more. Now we're up to 172,000 instances of that word. This demo is a little old. We just added or just got support for counter columns. So this demo is using just regular columns and persisting numbers there, not using counter columns. But we do have counter column support. So this main method here is the entire, basically the entire code for that demo by reusing the out-of-the-box Cassandra bolts. So in our topology, like I showed you before, let me pull that up. We have a word spout, which sends words to a count bolt. Count bolt keeps track of those, and then when it updates a count, it sends a message to the Cassandra bolt to persist that count. And basically, in this line, we're setting up the Cassandra bolt and using a default tuple mapper that's using strings for persistence. We do support different types of serialization. For these demos, we're mostly just sticking to strings. And as I mentioned before, Storm supports guaranteed processing, and part of that is when a tuple passes through or when a tuple gets emitted from a spout, if you've defined your topology to be guaranteed processing, then all those tuples must be, the whole tuple tree must be ACT. And the Cassandra bolt supports different ACT strategies. So in this case, I've used ACT on write. And what that means is as soon as the data gets written to Cassandra successfully, the tuple will be acknowledged. And once it's acknowledged, then the spout won't be triggered to re-emit that tuple. The next line's down here. This is where we build our topology. Here we're saying, creating a new topology builder. Then we're saying, setting the spout to be our word spout. And this last number over here is the parallelism. So what we're saying there is when we submit that topology to the storm cluster, we want 3 parallel instances of the word spout. Then we go on to set the bolt, first bolt to the Cassandra count bolt. And that's just a generic Cassandra bolt that we configured earlier. Again, we're saying a parallelism of tree. And then here's where we tell it to use a fields grouping and that it subscribes to the word spout, and then which fields we're using for that grouping. In this case, just the word. And then finally, this is where we set up our Cassandra bolt to subscribe to the count bolt. Okay. The next demo is for distributed RPC calls in Storm. While there are cases where you have streams of data that are open-ended, like I just demoed, DRPC in Storm allows you to create a request-response type interaction and essentially distribute out that processing to your cluster. So for the way that works in Storm is you have a DRPC client that passes in args to a DRPC server, and the server sends out tuples via a DRPC spout. That's a special kind of spout. And then from there it goes into your topology that you define. So it keeps track of that by request ID, which is ultimately how that the result will get returned to your client. So the spout emits to your topology, and then the result from your topology goes back to the DRPC bolt, and the bolt will notify the DRPC server when the computation is completed, and then the result will get returned to the DRPC client. So another example, if I have 3 followers and I tweet a URL, the reach would be 3. But then, let's say someone else tweets the same URL, and depending on the number of their followers, then the reach would be the net sum of my followers and that other user's followers. So to do that at Twitter, where there are massive numbers of users, that would take a lot of database lookups and a lot of performance hit if you're hitting just a single database. So what we can do is we can take that and break it down into a DRPC topology. So essentially our input to that is a URL, and that goes to the tweeter's bolt, and that essentially takes the URL and does a lookup of how many users tweeted that URL. So all those get, so all the records of that tweet then get shuffle grouped to another bolt, the followers bolt, and that takes the number of followers, or I'm sorry, the user ID of each follower and emits that out as a tuple. From there, it goes to a partial uniquer, which uniques those, and finally it sends the result of the uniquer to a count aggregator, which will count how many users have been exposed to that URL. So if I go back over to Cassandra, basically the model for this is, let's look at tweeters first. So this is basically a valueless column that has a URL and then a column key of each user that has tweeted that URL. Then if we look at the followers, the followers column family is again another valueless column, and the row key is the username, and then the column names within that are the users that follow that user. So this basically sets up your social graph. So when I run the Cassandra reach topology, you'll see storm startup. You're going to see a lot of logging information. And it actually completed already. Right there, based on what was in those two column families, it was able to compute the reach of the following 4 URLs.
Cool. So, go again.
So again, the code for this is, there's not a whole lot to it. Basically just set up our Cassandra bolts, again, reusing out of the box Cassandra bolts and mappers. So we set up a mapper for our tweeters and URLs, followers and tweeters, and then this code sets up the topology that I pointed out in that diagram.
Cool. Yeah. All right. So hopefully that was some pretty cool storm in detail, and you know, both of us are out there on GitHub. So if anybody has any questions, all this is out there, including the examples. So if you clone storm-cassandra, you'll see an examples directory in there that has all this stuff. So and if you have any questions, just hit us up. We can answer those. So next part here, we're going to talk a bit about Trident. So this is how I've been spending my days on Trident, because what happened is, and probably many of the questions out there might be around transactional integrity. You know, how do you not overcount stuff? How do you not process it twice? That kind of thing. So there were a bunch of patterns, I think, that were cropping up when people went to start using Storm. And underneath the hood, we said we had both a batching and non-batching version of the Cassandra. I mean, things are easy when you're only taking, you know, one event into account and then, you know, happily processing and moving along to the next one. When you start batching stuff, and you start considering fault tolerance, things get a little more complicated. So Nathan saw all those patterns, Nathan Marks Twitter saw those patterns and decided, hey, we can all benefit from creating a higher level of abstraction here and hiding some of the underneath the hood stuff that's required to implement exactly once and semantics and transactional integrity. So, so Trident in a nutshell, he took, like I said, state management, which is what gets complicated when you consider fault tolerance, and batching, and provided an API on top of it. So he created additional primitives where the primitives in Storm are the bolts, the spouts, and the topologies, all operating on tuples. In Trident, you have functions that are and state objects that are operating on Trident tuples. And effectively, we were early adopters in the transactional topologies, which have since been deprecated, because I think what Nathan's shown is that all the power that we had in transactional topologies, if anybody's been using them, is available in Trident, but from a much higher level of abstraction. So, all the classes that were in the Storm Kafka that dealt with transactional topologies are now gone in favor of Trident versions of those same classes. Trident is not something different than Storm. It is APIs in Storm. When you go to deploy Trident topology, it actually compiles down into Storm topology and runs. So, like I was saying, so it has a couple different primitives in Trident. One of those are the operations that you can perform, and what you can think of, what Trident gives you is it takes a stream of those tuples and partitions that stream into a set of batches. And then it provides operations on those tuples within those batches. And I just called out a couple kind of operations that you can perform. You can see how it's a higher level abstraction. So one of the use cases of a bolt that Taylor called out is the filtering. So instead of going and subclassing from bolt and implementing my filtering as a concrete class, I can just use a function here that implements a filter, right? So I just implement a quick function that says, should I keep this tuple? And my responsibilities to the filter are either emit the tuple or I don't emit the tuple. Likewise, a generic function, I take in the tuple and I can emit that thing again with additional fields in it or additional tuples. And then there are aggregate functions. So I can do what Nathan calls combining, right, which is pairwise combining of data, or I can reduce that, which is an iterative accumulation. So you basically keep a count, right, and then you pass tuples and adjust that count. Or even more generically, I can go, implement the aggregator, and that's sort of bring your own aggregation to the table. So this is a sample topology in Trident. It looks very similar to a Storm topology, but you can see, these are functions here like count and split that I just plug in. And then I basically say what my input is and then what my output is right in the topology. So very, very similar, and really the benefit of Trident is this. So the Trident state, Nathan figured out, I guess, a couple cool things about how to write state so that you can handle losses of nodes and batches. And the way that he did that is that state manipulation. So instead of just writing a value to the database, you write the ID of the last batch that produced that result, and then all batches are sequenced. So if you just wrote batch 3 and batch 5 is there, it's not going to write until it sees batch 4. And in that way, everything else in Storm is done in parallel, but the state you can be guaranteed to be in a good state because everything's written sequentially down into the database. And this is where we're headed with the Cassandra, storm-cassandra. And there's somebody else out there we should give a shout out to. I can't remember, Frostbite, Zero, something, Frostman, who's got an implementation of the Trident, the persistent map for Storm, and we've been using it internally. So that's been working out well, but we want to add some flexibility, so we'll probably reach out to Frostman to coordinate and collaborate with them. Anyway, so with respect to Storm State and how it applies to transactional integrity, there are two different kinds of spouts that you can have in Trident. One is called the transactional spout, and the guarantee there is that a batch or your obligation as a spout implementer for a transactional Trident spout is that the batch contents never change. So we use Kafka here as our main spout for all the work for our topologies. So there's a transactional Trident Kafka spout that is guaranteed to emit the same batch, the same tuples in the same batch each time. And for reasons I won't go into now, that's not so great if you lose a node, because if you have multiple partitions emitting, you could lose a partition, and then you wouldn't be able to have the same tuples from that partition in the same batch. But we can save that for another time. Or you can have an opaque spout where the batch contents can change. But in that scenario, you have to be very careful with your state, and there's additional obligations on the state object if you want to maintain transactional integrity. So I'll go through that now. So like I said, so these are sort of the contracts established by Trident for spouts. So one case, the batch contents can never change, and the other they can change. That has implications to the state. So just like spouts, there's transactional and opaque state management. And in the transactional state, the transaction ID is stored with the value in your state object when you persist to the database. Each batch has a unique transaction ID, and like I said, that trick works then, because what I can do is every time I update the state, I just write the last transaction, my current transaction ID, and I don't write until the previous transaction ID is written. And if batch contents never change, then that's great, that works. That doesn't work, however, if the batch contents can change, right? So in that case, what your obligation is to create a state object is to write the previous value and then the last transaction ID and then the current value. So this says that if a batch gets replayed, I can replace the value that's in the database with what I've calculated from the new batch. With that, you can get exactly one semantics from Storm with combinations of the spouts and states. So we probably should have included a few more slides. That can get a little tricky. I should have given a couple demos, but maybe we can come back and do another session on that when we iron it all out. Okay, so in order to give some time for questions, here's the shameless shout-out slide. So here at HMS, I didn't go through the full architecture topology that we have in place, but we have two bolts that are out there now, the storm-cassandra bolt, which we've been talking a lot about. We also have storm Elasticsearch. So by combining those two, you can actually have a data processing pipeline that writes to Cassandra plus enables fuzzy search on the other end if you tack that Elasticsearch bolt onto the end of your topology. And then internally, we haven't released it to the public yet, but we also have a Storm JDBI bolt, so that allows you to tie in the relational database. So if you go back to that picture from the beginning of the slide, you can tie in your favorite relational and enrich the data that's coming through your pipeline with any kind of metadata that might be stored in a relational database. Or you can write to the relational database that supports reporting tools. And then Taylor's got two other ones out there, Storm JMS and Storm Signals. I don't know, you want to talk about Storm Signals? It's basically, go ahead.
Sure. Storm Signals is basically, it allows you to communicate with your spouts and bolts out of band. So, for example, let's say you have a topology and you want to send it some sort of signal to change its behavior or something like that. Storm Signals just gives you a very simple way to do that. And everything that we demoed today is all part of the storm-cassandra project. You should be able to get up and running with those examples in about 5 minutes. So it's all there on GitHub.
Yeah, if you can't, let us know.
Yeah.
And just a couple of closing remarks. I mean, what we've found is that, and I've always believed Cassandra provides great primitives that allow you to do distributed storage. So we've found that the data model that's provided by Cassandra and the way that it partitions up the key space, right, automatically across hosts is perfect, absolutely perfect. And I think Storm is a natural fit to that because what it actually provides is primitives for distributed processing that you can do a lot with and combine in any kind of creative ways. So, those two together create a pretty good basis on which you can build, any kind of big data platform. And then one last piece of that is that if you go back to Taylor's demonstration of DRPC, right, some of these, and like Hadoop and some of these distributed processing systems, they're mostly focused on asynchronous cases, but the DRPC allows you to also do things synchronously. And there's tons of cases where that becomes really applicable, where you want your answers to come back in the same request. And one of the things that we're trying to do is figure out how to reuse topologies across both asynchronous and synchronous means. So if anybody has any thoughts on that, we greatly appreciate them, especially in the Trident world. So I think that's it from us. We got a few minutes here for questions.
Thank you, Brian and Taylor, very, very much. So please feel free to ask your questions in the Q&A tab or in the general messaging window. While we're giving a couple of minutes to the questions, I wanted to just go over a couple of things here on our slides of upcoming events. So, this is one in a series of webinars. We always archive them. We want to help the community by putting out some great content, and Taylor and Brian have put out some great content today. Next up is Christos Kalantzis from Netflix is going to talk about his transition from being a DBA of relational databases to now really leading the charge of DB engineering by moving to Cassandra. He'll address other NoSQL databases as well. And then make sure you mark your calendars for Valentine's Day. It's not, V is not for Valentine's, it's for vNodes. That should be a very hot topic. That's by Patrick McFadden. And then on February 28th, Aaron Morton will take a look at an introduction to Cassandra, and we'll be focusing on the recently available 1.2. Some resources we have. 3 weeks ago, we released Planet Cassandra. That is the community site. The community is doing a good job centralizing stuff there, so that's sort of your one-stop shop for everything Cassandra related. This webinar will be available there. If you're interested in more deep dive training around Cassandra, visit our training page. And then Brian and Taylor are going to be talking at this one. NYC Star, March 20th. If you're on the East Coast, definitely try and make it down for this technical day around Cassandra. Okay, so are you ready for questions?
Yes.
Yes.
Okay, great. Are there any CEP alternatives to Storm that you're aware of that also work with Cassandra? You did a good job talking about Solar and Elasticsearch and a little bit of the differences. Did you guys look for anything else other than Storm?
That's a great question. I've seen I should say not to my knowledge. That's kind of a hard question to answer though, because there are tons of event processing systems, and I think you could tie any one of them to Cassandra if you wanted to. We preferred the abstraction that Storm provides. But I should say that there's been a lot of activity over the last week and a half, probably on the discussion list around other DSLs, so domain-specific languages that would allow you to articulate processing your processing flows that would compile down or eventually become storm topologies, right? So there's been a lot of discussion about making an Esper-like language that would compile down into Storm. We've also seen some people working on Drools, so that would leverage Storm on the back end. So I think I can imagine what that is, right? That's a bundling the Drools engine so that it deploys probably in bolts and can read the rules language that Drools has. So it's kind of a hard question to answer, but I think a lot of people are looking at Storm. It certainly has the most momentum. I forget, it's like 6,000 followers and 500 forks or something like that on GitHub. So it's certainly got the most momentum, and I think everybody, Nathan's got a cascading background. So if you look, cascading is another one, but cascading compiles down into Hadoop. So he took the best of cascading and made it real time.
Okay, great. That's good to know. And yeah, just to reiterate, we're seeing this combination of Storm and Cassandra more and more out in the Cassandra community. Going back to your, I think this references back your sort of architectural slide up front. In a multi-data scenario, will Zookeeper only look after the local slaves, or will it be aware of all the slaves in all the data centers?
And actually Zookeeper doesn't look after the nodes per se. Zookeeper is essentially just houses the stored state of the system, and it's Nimbus that communicates with the nodes through Zookeeper. But how that set up is basically however you want to configure it. So Nimbus finds out about additional nodes through Zookeeper. Hopefully that answers the question.
Yes, thank you very much. This one, can you talk about this data pipeline use in production, your volumes, hardware, and the unique value Cassandra provides versus other NoSQL options? So, I'm assuming you can integrate Storm with other databases.
Yeah.
Can you focus on the unique value of Cassandra?
Sure. Yeah. So, when you compare, and this goes with Elasticsearch too. So, our architecture, what we want out of it is linear scalability, right? So, we've got a legacy system here that has got upwards, I don't know, probably 100. We've got hundreds of machines here. So, linear scalability is really important to us, and Cassandra nailed that, absolutely nailed it. So every other piece of our architecture we want to scale linearly like Cassandra, right? And I think that, if Storm does that, Elasticsearch does that, so when you look at Cassandra versus others, you're going to start to get an impedance mismatch if your processing framework scales linearly, but your database under the hood can't support that, right? So if you had, a relational database, you'd have to figure out how to shard that thing and have it interact properly. Or if you have a relational database, that they're notoriously hard to scale linearly. So it just made a lot of sense that if we've got a processing framework that can scale linearly and an indexing engine that can scale linearly, why wouldn't we have a database that can also do that natively, right out of the box with a little admin?
Great, thank you very much. And we're coming up on the top of the hour, but maybe we can sneak one in. So you talked about going to GitHub for the code. What about educational resources around Storm specifically? Where are some good places to go?
Storm is also open sourced on GitHub, and I'll type in the URL for that in the chat area. So that URL, that's the source code for Storm, and there's also a very good wiki that covers all the basic concepts behind Storm.
Okay, great. Thank you very much. We're right at the top of the hour. Really appreciate you taking the time today, guys. Great topic, and you know, this has been a great session to educate the community. Stay tuned, everybody, for more upcoming webinars, and we will see you next time. Thank you very much.
Great. Thanks, Christian. Thanks, guys.